let's solve a truss using the method of sections. Before we do that, let's just remind ourselves of the procedure, since this is the first tutorial on this topic, and then let's solve this truss here. All right, let's dive into it. We'll start off by looking at the procedure. For solving trusses using the method of sections, just like before, we'll check first that the truss is determinate. Once we've done that, we will find the support reactions. We will then create an imaginary cut through the truss and separate both parts of the truss. We need to remember at this point that only 3 non-zero force members can be cut. Once we've done that, we will draw the free body diagram, including the internal forces in the cut truss members. We'll assume that all internal forces are in tension, just like we did with the method of joints. We'll then select one part of the truss. We'll tend to select the easiest part to solve, so this could be the part with the fewest forces or the part with the most convenient geometry. And once we've done that, we'll solve the internal forces using 3 equilibrium equations. We'll try to achieve only one unknown force per equilibrium equation, just make it easier for us to solve. And we can do that by using a few different possible sets of equations, and I talk more about that on the lecture on method of sections. So now that we know the procedure, let's solve the truss using the method of sections. This is the exercise we're going to solve. We can see here that we have a truss with a pin support at joint 1, a roller support at joint 3, and we've been asked to find the forces in specific members, member 1, 2, 2, 4, 4, 5. But before we do that, we need to check that the truss is determinate. So let's start off with that. So to do that, we need to figure out what are the unknowns and what are the knowns. So the unknowns are always going to be the number of reactions and the number of members. In this case, we have 3 reactions and we have 9 members. Okay, that gives us a total of 12. And knowns are always going to be the 2 equations per joint. So 2 times the number of joints, and in our case, that is 2 times 6, and that is also 12. And that means that this truss is determinate, and we can solve it using the method of sections. Now for the reactions. To do this, I am going to create my free body diagram. So I am going to replace this pin support in place 1 with 2 forces representing the reaction forces, so V1 and H1. And I'm also going to put the reaction force in place of this roller support, and that is going to be V3. Now that I have my free body diagram, I am just going to confirm my sign convention. So I'm just drawing here the positive directions for me. And after I've done that, I see that the easiest is to start off with the sum of forces in the x direction. So in the x direction, I have H1, and I actually don't have any other forces, so that means that H1 is 0. I'll now move on to doing the sum of moments around joint 1. And the reason that I'm choosing joint 1 is because I see that V1 and H1 pass through that joint, and therefore they won't contribute to moment. So what I have is I have V3 contributing a positive moment times a distance of 10, and I have the 20 contributing a negative moment times a distance of 5. And if I isolate V3, I find out that V3 equals 20 times 5 divided by 10, and that equals 10 kilonewtons. I can now go on to do sum of forces in the y direction equals 0, with this being my positive direction. And here I have V1 plus V3 minus 20 equals 0. So V1 is going to be 20 minus V3, which I just found is 10, and that leaves me with 10 kilonewtons. And before I move on, I am just going to replace these forces that I've drawn with the results I've just found. So H1 came out as 0, so I can just delete that completely. V1 came out as positive 10, so there we go. And V3 also came out as positive 10, so just putting that in there. Now that we've solved the reactions, we can move on to the next step, which is making our imaginary cut, exposing the internal forces, and solving them. Let's look at the truss and see what members we were asked to find. Okay, what I'm going to do first is I am going to check where are these members that I need to find the forces in. So I've been told that I want to find the force in this member here, 1, 2, in 2, 4, which is this member here, and 4, 5, which is this member here. I mean, that really already gives us where I'm going to cut. So I'm just going to make a cut here through these members. Now that I've made the cut, I'm going to separate these into two parts of the truss. So I'm going to have the first part, which will be this part here, right? It will consist of these members that I've just cut. There is also this force of 10. And the other part of the truss is going to be this part here, with this part completely intact. And here I'm going to have the other members that I've cut. I'm also going to have the force of 20 here and the reaction force of 10 here. Now I need to express the internal forces. So I'm going to assume that they are all in tension, which means that this is how they're going to look, right? This here is F4, 5, this is F2, 4, and this is F1, 2. And now that I have this, I can completely discard the side that I'm not going to be working on. Now, I am going to choose to work on the left-hand side, and that's because it just has less forces. And that's my only reason. So let's just discard the right-hand side, as we won't be needing it for finding these internal forces. So now I need to write 3 equations of equilibrium to find them. Before that, I'm just going to do one last thing, and that is finding this angle alpha here. I know that I'm going to need it in my calculations, so I better just find it now. So I'm just going to do that by figuring out that tan alpha is 4 over 5. And if I go inverse tan 4 over 5 on my calculator, I'll find out that this is 38.65 degrees. And I'm ready to start. If I look at this structure now that I have to solve, right, this one here, I can see that there is only one unknown thing, that is 2, 4 in the y direction. So I'm going to start off with that. I'm just going to remind myself here what my positive directions are. I just want to be consistent with them as I go through this. So I'm going to start off, as I said, with Fy equals 0. And so I've got 10 in the positive direction, and I've got minus F24 sine alpha in the negative direction, right? And just a reminder that if that was alpha at the bottom, this is alpha here, okay? So F24 is going to be 10 divided by sine alpha, and that will work out as 16 kilonewtons. I'm now going to do moments around joint 2. Joint 2 is really, if I kind of draw this in, is this joint here where these two meet, okay, where 2, 4 and 1, 2 meet. Now it doesn't matter that that point is not on this little drawing that I drew, right? Because the fact that this needs to be in equilibrium is relevant for every place in the space. So I can do my moments wherever. So I'm going to do them around joint 2. F24 and F12 pass through that point, so won't contribute to moment. And I'll be able directly to find what F45 is. So sum of moments around joint 2 equals 0. And here I have minus F45 times 4. and minus 10 times 5 equals 0. So f45 equals minus 10 times 5 over 4, and that will give me minus 12.5 kilonewtons. And the last thing that I'm going to do, I am going to do sum of moments around joint 4, which is this joint here. And the reason that I'm going to do it there is F45 and F24 pass through that joint, so they won't contribute to moment, and I'll find F12 directly. So sum of moments around joint 4 equals 0, and here I have F12 times 4 and nothing else, because as we mentioned, F45 and F24 pass through that joint, but the line of the reaction of the 10 also passes through that joint and therefore also doesn't contribute to moment. So that equals 0 and F12 equals 0. I could have known from inspection that F12 is a zero force member. If you want to recap on that, go to the lecture on the method of joints. But what I found here is that F24 is 16, came out positive, so it's in tension, and F45 is negative, so it's in compression, and its force is minus 12.5 kilonewtons. And F12 is a zero force member. Thank you for joining me to solve this truss using the method of sections. I hope it's helped. If it has and you want to see more truss solving using either the method of joints or the method of sections, check out my other videos on the topic. Bye for now.